This video will cover section 4.8, applications and models of trigonometric functions, and this is for the class of 2412. The objectives for this lesson will be to learn how to solve real-life problems involving right triangles, also to solve real-life problems involving directional bearings, and the third one, to solve real-life problems involving harmonic motion. In this section, the three angles of a right triangle will be denoted by the capital letters A, B, and C, where C is gonna be the right angle, capital letter. And the lengths of the sides opposite to these angles will have the letters A, B, and C in lowercase, respectively, where C will be the hypotenuse. So let's illustrate this. Please write it down on your notes. So if this is my right angle, this is going to be labeled as uppercase C for the angle, and the side that is opposite to it is going to be lowercase c. Remember, with Pythagorean theorem, we also use c to denote the hypotenuse. And so hypotenuse is always opposite to the right angle. The bigger the angle, the longer the side of the triangle. That will be opposite to that angle. I don't know if that makes sense. Anyways, so then we will have, let's see, I believe, well, we're starting with C. Let's just go ahead and call this one A. And so the opposite side to angle A will be lowercase a. And then finally, if this is angle B, then the side opposite to it will be lowercase b. Example 2. A safety regulation states that the maximum angle of elevation, remember, angle of elevation, we went over that definition. It is the angle that is made with the horizontal and, well, I guess I will just trace it here. So that will be the angle elevation from the horizontal and then kind of like looking up. So the regulation states that the maximum degree for that angle will be 72 degrees for a rescue ladder. And the fire department's longest ladder is 110 feet. And that will be the length of the ladder. Perhaps here is without being fully extended, because here they're marking it at 110. However, if you were to perhaps imagine the truck gets closer to the building, then the ladder could be fully extended and maybe form like a 90-degree angle right there. But that is not within the regulation. The regulation states that that maximum angle could be 72 degrees, and that is what we have here. So I'm going to continue reading. What is the maximum safe rescue height? So the question is about what is the height. And so perhaps it will not be as high as we are highlighting here on the image, but we're going to find that exact number so that it is still within the regulation. So what I like to do in this case is I like to draw my own triangle, because sometimes that drawing could be a little distracting. It's also a good practice for when you don't have a drawing at all and you have to come up with your own. So what we know so far is that the angle here is equal to 72 degrees. This side is 110 feet. And what we are looking for is this side. So now, corresponding to this angle here, the side that is opposite to it is A. So we have an opposite side, and we also have the hypotenuse. And so what type of trigonometric function out of our 6 trigonometric functions will require us to use opposite and hypotenuse, or is defined as opposite over hypotenuse, and the answer is sine. And so we happen to have an angle right here, so the sine of 72 degrees. Now, can we solve this? Yeah, absolutely, because we do have an angle, but we also have one of the measurements. And so if you have two things, you could solve for the third one. So the sine of 72 degrees is equal to A. Instead of opposite, I'm going to use the letter A, divided by the hypotenuse, which is 110. So now if I want to solve for A, which is representing the height, the maximum height, I will take this 110, which is dividing to the A. I will take that across my equal sign, and the inverse operation for division is multiplication. And so that is what's going to happen once I move the 110, or you could think of this of us multiplying by 110 on both sides. The reason I don't write it down is because I just think it's a waste of time. We know it's going to cancel, so why write it down? Now from here, we can enter that on the calculator. So we're going to enter 110 times sine of 72 degrees. And I know my calculator is in degrees because I can see it here on the screen, or you could see it here. But if you are not sure, you could always go to mode and you could check there. And as you could see on our screen, the word degree is the one that is highlighted. So I'm going to go back to my main screen. And now I'm going to press enter. And so the number that I get is 104.6162. So let's see how we are expected to round when we give our answer. As you can see, we're not being told how to round, so I'm just gonna, the answer was 104.6 something, so let's just round one digit after the decimal or to the nearest tenth, and the answer will be in feet. And so that will be the maximum safest height that the ladder could be used within the regulation for that particular city. Now let's talk about trigonometry and bearings. In surveying and navigation, directions can be given in terms of bearings. A bearing measures the acute angle that a path or line of sight makes with a fixed north-south line. So let's go over what is the north-south line. And I think you already know the answer, north, south. So in terms of X and Y, imagine that the north-south line is the Y-axis. And so we always start from there, and it's kind of different from what we have been doing, which is angles and standard position, because they do, in case you forgot, they do start at the positive x-axis. So for bearings, we're not going to do that. We're going to start from the y-axis, or actually the north-south line. So because of that, a bearing will start with the letter S for south, or north, N for north. Or here you can see the letter N for north. So let's go over the first example. And the answer is already written there. So it says, for instance, the bearing south 35 east shown below means 35 degrees east of south. So we start here, S for south, and then we go in that direction that you see the arrow pointing to because we're going in the east direction. So we go this way, and how far do we go? 35 degrees. So that will be south 35 east. Now, within this same example, I would like to graph perhaps how north 35 east will look like. And so that would be something that starts from north. That will be the initial side. And then we move in this direction because we're moving towards east. And that will be the terminal side. So you see the difference from north and south is where will your initial side of the bearing will be. Okay, so let's move on to our example on the right side. And for this one, we're gonna write it in words, but first let's see what it says. So north, and so that's why we start here. By the way, we always have to have an origin set. Then we start at north and we go 80 degrees, but in the west direction. And so that's why we go in this way. And here is the terminal side of that bearing. Now let's do something a little different. So let's graph north 80 degrees west. Well, that will be the same. That's not what I meant. Let's change west for east. So I will start here at north and then go 80 degrees, but towards the right because I want to go in the east direction. And so that will be the difference. Now let's write this in using words, and let's just focus on the example that we were given, this one. And so that will be, I'm going to try to copy from the other one. So that will be, okay. So for this one at the bottom, it will be 80 degrees. Remember, I'm working on this one. West of north. But we always start from the north and then 80 degrees in the west direction. Okay, and we have one more example here. And so that will be, it is written here at the bottom, and it will be north 45 east. So we start here, north, and then 45 in the east direction. And so that will be the bearing. And remember, we all have to have an origin. Example 5, finding directions in terms of bearings. A ship leaves port at noon, and that will be here. Noon will be at 12 p.m. and heads due west. Now here we don't have anything like north, 30 west or anything like that. So if it says west, you will just simply follow horizontal, well, I guess, yeah, in the horizontal direction, you will go towards west from the starting point. So in this case, we started here and then the ship went due west at a speed of 20 knots or 20 nautical miles (nm) per hour. Now, this is important because we have the 20 represented here, but it's being multiplied by 2. The reason for that is the next sentence. At 2 p.m., the ship changes course. And I'm going to pause there. So if we started, or well, the boat started traveling at noon, by 2 p.m., 2 hours had passed. And so 2 times 20 will give us 40. So the distance that was covered was 40 miles. Okay, or nautical miles. Then at that point, the ship changes course using this bearing, north 54 west. So I am going to trace here. I'm going to use this as my origin, and I'm just going to trace, I'll erase it in a minute, north-south line, and so that we could get the correct visual. So it says north, so meaning we go up here, right? North, and then 54 degrees. That was probably not a good color choice. So north 54 degrees, and now it starts going in this direction. North 54, and it's also west. So that's why we kind of moved to the right, because west is, I'm sorry, I said right. I should have said left, because that's where west will be. If this was north, south, west, and east, that's what it means. So we keep traveling in that direction, and then in this case, the speed is the same, 20 knots or nautical miles per hour, and then the problem keeps saying, find the ship's bearing and distance from the port of departure at 3 p.m. So from 2 p.m. to 3 p.m., it was just 1 hour. Since the speed was 20 nautical miles per hour, this one, the length or the distance will simply be 20 nautical miles. So the question is to find the distance from the port of departure, which was here, point A, and oh yeah, from where the ship is right now, right here. So from point D to point A. And so that distance will be the length of, in this triangle that we see here. Okay, now the triangle that I have traced so far, you could see that is not a right triangle, and it is an oblique triangle. So we cannot use our trigonometric functions to solve that. But as you can see with the drawing, we could do something and then get 2 right triangles out of it, out of both. So I'm going to show you how to do that. So if I was to draw the same triangle, I will start here at the starting point or departure point, and then I will travel west for 2 hours at 20 nautical miles per hour. I know that's not a straight line. I'm going to redo it. Okay, but remember, this is my starting point, so I should be going in this direction, west direction, for 2 hours at 20 nautical miles per hour. So then, and actually, let me write the units here so you see where they are coming from. So this will be 2 hours, 20 nautical miles per hour. And so the units hour cancels, and so that's why we say that is 40 nautical miles. Okay, at that point, we decide to turn in the north 54, sorry, west direction. And then at that point, I will continue to go this way for 1 more hour, because that happened from 2 p.m. to 3 p.m. And so at that point, 1 hour at 20 nautical miles per hour, it will just give us a distance of 20 nautical miles. Okay, at that point, we stop, and now what we are asked to find is the distance that I'm tracing right now. Oh, that's not good. The distance from this point, oh, not good either. I'm gonna just pause the video. Okay, so I have my line, and we are going to call that distance from point D, where the boat stopped. So from that point to point A, from where it started. And we're going to call that C, lowercase c. I'm just following the drawing here. Okay, so what we're going to do is create a perpendicular line. Like if we were to extend this one, and then we connect it with a perpendicular line coming from point D. And we're going to refer to that vertex or the angle here as C. Okay, now I want you to use your imagination, and you are going to see two right triangles. One of them is here. So what does that mean? That we could actually use trigonometric functions. And what do we need? Well, we have one of the sides, but that's all we have. We don't have one of the angles, except for the one that says 90, but that's not very helpful right here. However, we do have something that came out of the bearing here. And you can see it here. The bearing was 54. So because this angle here happens to be a right angle, and we know it is a right angle because we drew the north-south line to be perpendicular to the trajectory of the boat. So that is a right angle, and if this little part is 54, we could find the complement, so 90 minus 54, that will give us 36 degrees. So the angle that we need here, it's going to be equal to 36 degrees for this angle. Okay, and so from there, I'm gonna erase or delete some stuff here so it's not so cluttered. And now I'm going to trace the other triangle, right triangle. So that one's going to be formed by this line here, this line, and this one. And there we have two right triangles. They are both sharing this side that I'm highlighting, and they are also sharing that 90-degree angle. Now what I'm going to do is, since we have them labeled as A, B, C, D, we are going to draw them separately so it makes a little more sense to you. So for the triangle BCD, which is the one that I trace with the yellow highlighter first. BCD, the little one. C is here, B is here, and D is here. Okay. And we know this side is 20. We know this is 90, and this is the one that we found by getting the complement of 54, which came from the bearing. So that one is 36 degrees. Okay. Oh, and it's actually here, how we found that angle, B. So we are trying to find one of the sides that will help us figure out the length of lowercase c, the hypotenuse of the big triangle. And so what we need is to know what this side will be equal to. So let's call it B. And we also call it B because it is opposite to this angle, uppercase B. So lowercase b. Okay, so we need to find that one. And one thing we could do, we have the angle 36 degrees. We're looking for the opposite side to it. And we have the hypotenuse as well, which is 20. So the trigonometric function that comes to my mind, or ratio, will be sine of 36 degrees is going to be opposite, so it's b divided by hypotenuse, which is 20. Now, if we want to solve for b, which is kind of like what we need to do right now, solve for b, we're going to take that 20, and which is dividing on the right side. So then once we take it across, it's going to be multiplying. So it will be 20 times sine of 36 degrees equals b. And that is what we have here. Now we're going to take the big triangle, or in fact, no, not yet. We need to find the measurement of the other side. Why? Well, because we know that this part here we know is 40, but we do not know the length of this one. And so that one we can find it by using the little triangle. Why do we need that one? Well, because for the big triangle, we're going to need both. The one that is 40 nautical miles long and the one that goes from here to here. And so that one, since it's opposite to angle D, we're going to call it lowercase d. Okay, so now D is the adjacent side to the angle that we have there of 36 degrees. And so what makes sense for us to do is to use something with the adjacent and the hypotenuse. And that will be the cosine of 36 degrees is equal to the adjacent side, which we're calling D, over the hypotenuse, which is 20. Now, if we want to solve for D, it will equal to 20 times the cosine of 36, because remember 20 is dividing on the right side, on the left side it will be multiplying. Now, that is what we have here. And yes, these two expressions are exactly the same. It doesn't matter if you have your variable on the right or on the left. So now with those two expressions that we have, we're going to enter those on the calculator. So I enter the two expressions into the calculator, and you could see that I do not get an exact number. I get an approximation. So that is not really good when we're using problems that have multi-steps, more than one step. So, and the problem is that we don't know exactly how to round it, and perhaps we might round to the nearest integer or to the nearest tenth or hundredth or thousandth or so on. And so when we start rounding like that, we start getting further and further from the exact answer. And so instead of using decimals here, what I'm going to decide to do is keep my trigonometric expressions like that. Just for fun, we're going to write a quick approximation. So 11.75 and 16.18. So the same big green triangle that we have here, I have attempted to draw it again so we could see it down here. And so let's go over it again. The question is to find this value here, lowercase c, which is the distance from point D to point A. That's what we're trying to find. So we're going to use this right triangle. And remember, we use the little triangle to find the value for B. However, instead of using the approximation, we are only going to use the trigonometric expression. So instead of B, we use 20 times sine of 36 because we don't want to start rounding too soon. Okay, similarly, instead of using oh, yeah, and we discussed how we needed to know the distance from here to here, D, so that we know the base of the big triangle, because so far we only know that part of it is 40. But we need to know what the other little piece was. And we found that by using the little triangle, and we call that lowercase d. However, we're not going to use the approximation that we see here. We're going to use the actual trigonometric expression. So we're going to use those two instead. Okay, so now we know those two sides. We know two sides of this triangle. So I'm going to call the opposite side, which is B, it's going to equal to, let's just call it B for now. Opposite is B, and the adjacent side, and I'm going to be using this angle here, the one that is formed from the segment AD to AC. So this is the one in question. And the reason we're using that is because it's also part of our question to find not only the distance, but also to find the ship's bearing. And so that will be the bearing from here to here. And that's why we're using that angle, which is the angle from here to here. So let's go back to that one. And if that is called angle, I'm sorry, I'm calling it theta. We're supposed to call it A. And so that is angle A. And since we have an opposite side and we also have an adjacent side, and that adjacent side we know is 40 plus D. So 40 plus D. That's our adjacent side. So which trigonometric function is defined as in terms of opposite and adjacent? So we have two, tangent and cotangent. It's a lot easier if we use tangent. So because tangent is opposite over adjacent, and we're saying that opposite is B. Opposite right here is the letter B. And we're saying that the adjacent is going to be 40 plus D, which is this whole side. 40 plus D. And that is what we see here. Or D plus 40, same thing. Okay, so we already agreed that instead of using the approximations that we see here and to the right, we will use the trigonometric expressions. So for B, we replace that with 20 times sine of 36. That's coming from here. And then for D, we're going to replace that with 20 times the cosine of 36, just like that. And then 40 is that piece that we already knew from the beginning of the problem. Okay, so now we have an expression that looks like this. Tangent of A is equal to 20 sine of 36 degrees over, I'm just copying the same thing, 20 cosine of 36 plus 40. All right, so now for us to be able to solve for A, we're going to need to find the inverse of tangent, and that will be tangent inverse of tangent. And so in this case, it's like we are actually writing it. I'm going to actually write it down twice. So tangent inverse of all of this. And so I'm going to enter this on the calculator, but I want to warn you that I'm going to be using extra parentheses, because if I don't, then I will not get the correct answer. And so I need to ensure that my numerator is in parentheses, and so is my denominator. And of course, I'm going to be using the tangent inverse key. So I'm going to show you with the calculator how you will enter this. Because I need to find the tangent inverse, I need to look at the key that says tangent, and it says tangent inverse with blue. That means I need to use the second function key. So I press that first and then tangent, and you could see on the screen tangent inverse appears. Now that one parenthesis there is the same parentheses that we have here. So I still need to open another parenthesis because I told you we want to enclose the numerator. So I'm going to open another parenthesis, and then I'm going to enter 20 sine of 36. I'm going to close parentheses to close the angle, another one to close the 20 sine 36, and then I'm going to enter, press the division key. I'm going to open parentheses. Again, those are the parentheses that you could see here in blue. And now I'm going to enter 20 cosine 36 plus 40. I close 30, after 36, I close it because that's closing the angle. And then plus 40. And then close the parentheses one time to enclose the denominator. So it's like I'm closing this parentheses that you see here in blue. And then I need to close it one more time so that I finish telling the calculator where to stop calculating the tangent inverse. So one more closing parentheses. And now I'm going to press enter. And that's what I get, 11.A185. So what does this mean? It means that here we could cross tangent, inverse, and tangent compose. They will outdo each other. So then the answer here is just A. So we got A And then the answer that we got from the calculator, the 11.81, I believe it was a 5, we're going to go ahead and round it to 11.82. I'm just following the PowerPoint. So then we're going to say that that angle A is 11.82 degrees. Now, that is not the bearing angle. And so to find that, we're actually going to have to use the complement of it, because at that point, if we trace the north-south line here, we know from here to here is where we got the 11.82. But for bearings, we need something like, let's say, north, and then we will need the angle that comes from the north-south line. So in this case, it will be north. So it will be north something, and since we're going to the left, it will be west. Yes, west. Okay, and so to find the complement of that angle, we have it here. We calculated 90 minus 11.82, and we get 78.18. So the bearing that we needed, so from here to there, is going to be north 78.18 west. Now we have one last thing to find, and that is the value of C right here, the distance from where the ship ended and from where it started. So to calculate that again, we use our big triangle, and since we already know the angle that we see here, 11.82, we could use that one. Or let's see, I don't think they are using that one here. They're using something else. So yes, we are using that one. I was just confused about the 36, but let me explain this to you. So considering the big triangle, I'm going to trace it here again, but not as big. So let's see, we have it here, here, and here. So we know this is B, and then we know this is D plus 40, and then we know this is C. And we also know that this angle is 11.82. So at this point, I want to concentrate on B and C. That's all I need. And so which trigonometric function requires opposite, because B is opposite to that angle, and hypotenuse? And so yes, it is sine. So the sine of 11.82 degrees is equal to opposite, which is B, over hypotenuse, which is C. And if we want to solve for C, we will have to get it out of division first. So we could move it across. It will be multiplying, so it will be C times the sine of 11.82 degrees equals B. And then again, we want to solve for C. So what is sine of 11.82 doing to C? And the answer is multiplying, right? So we are going to take that whole expression across the equal sign, and it will be dividing. So now we have B divided by sine of 11.82. So, and that is what we could see here on the left side. So we have that C is equal to B over the sine of A, which is, we already have it here, is the sine of 11.82 right here. Sine of A, this is angle A. Sine is opposite over hypotenuse. And, oh yeah, it's because we already solved for C. And so if we enter all of this on the calculator, we will get 57.4. So let me show you how you can enter this on your calculator. So you might want to open parentheses 20 times sine of 36. Make sure your calculator is in degrees, and then press the division key, and then sine of 11.82. In fact, you don't really need the parentheses here after the division key. And so if you do that, please check that you get the correct answer, which is 57.4 nautical miles, and that will be rounded to the nearest tenth. Harmonic motion. The period nature of the trigonometric functions is useful for describing the motion of a point on an object that vibrates, oscillates, rotates, or is moved by a wave motion. So I want to give you an example, and I'm not a physics person, so I hope I don't ruin this for you, but imagine that is a spring, right? And so I'm gonna move on the bottom, I'm gonna move that green button, and you could see how the spring is being stretched or is being compressed. And you could see that right there. Okay, so the blue bar graph that you see on top, that is just graphing the potential energy. We don't need to worry about that one because we're not in physics. But I want you to worry, not worry, but look at what happens to the displacement when I move it from 0 to 1. And so it's going to go like that. It's being stretched. So it moves to the right. And then I can go back to 0, and that could be its equilibrium point, and then I can move it back to -1. Okay, we could also have something that it's starting there at equilibrium, and then we move it, stretch it. And so with that, if we were to graph those the displacement at per I guess second, we could see if we put all those distances together, we will be graphing something like a sine or a cosine wave. I will show you one more simulation of harmonic motion. So we're going to place a weight on the spring, and then we're going to let it go. And so you see that back and forth, up and down, stretching, compressing. If you graph those distances, you will come out with a wave that resembles the sine and the cosine graphs. And remember, we established that they are the same, they're just shifted 90 degrees or pi over 2 horizontally. So what happens if I put a weight that it's less, a weight's less than the other one? So you see the motion changes. And so you will study more of this in physics. Hopefully you take physics. If you do, good luck with that. And in case you are interested in this amazing website, let me show you what it is called. It is called PHET, P-H-E-T, and it is from the University of Colorado. So the vibrating, oscillating, rotating, or wave motion, like I've been saying, if we graph them, we will create a sinusoidal graph. And of course, those could change the period, or the amplitude might be different. And so we're going to introduce two new words, frequency, and the other one, I forgot what it was, but we'll see it. So let's see. Just like the simulations that I was showing you, we could see on the first drawing on the left, the spring is in equilibrium and it's happening at, we're drawing purposely the distance here, or labeling it at 0. So that will be comparable to the origin. Then on the second figure, we can see the maximum displacement, and in this case we're going to call it negative, and we could see that is being represented by negative 10 centimeters. And when the spring compresses or coils back up, that will pass through the initial point, the equilibrium point, but it will go all the way back to the top, and that will be considered the distance from here to here. It will be considered positive, and it will be 10 centimeters, and that's what we will refer to as the maximum positive displacement. Now we're going to look at the pattern of the spring in a horizontal way. So recall that we start the equilibrium point, the starting point was at 0. Then the spring traveled down or below the equilibrium point 10 centimeters. So we're going to consider that 10. Then after that, it went back up. It passed through the equilibrium point, and then it went all the way back to the top, and the distance was 10 centimeters. Now here, the independent variable is going to be time. And the time that it took for the spring to go from 0 to its maximum displacement below 0 and then back again was 4 seconds. So we're going to assume that this is a 4. And so remember the intercept in between, actually, yeah, it's going to be the midpoint, the intercept, sorry, the intercept here is the midpoint between the maximum and the minimum point. So we have a 0 here, a 4 there. Actually, no. I believe what they're saying is that it will go, the spring will start at the equilibrium point, then it will travel down, it will go back past the equilibrium point, which is 0. It will hit the maximum positive displacement, and then it will go back to its equilibrium point. So that will be a 4. So now this makes sense. It's better. So then this intercept is 2. This is 0 for x. And so therefore this is 3 and this is 1. So, and this is all assuming the ideal conditions of perfect elasticity and no friction or air resistance. So the ball that is attached to the spring will be making that pattern going up, down, and then up, and then down and up, and so on, in a uniform and regular manner. So another thing that we could say is that if we relate this to amplitude, the amplitude is going to be the distance between -10 and 10, which is 20, divided by 2. So the amplitude is 10. And also we could see that the time it takes to complete one full cycle is 4 seconds. And so that is going to be the period. So from the concept of period, we're going to move on to another one, which is frequency. And frequency is actually on the next slide. It is defined as the number of cycles that it takes per second. So if you recall from our previous graph, a full cycle in length, in time, was the period was 4 seconds. So if we divide that 4 seconds by 1 second, or I'm sorry, if one period took 4 seconds, then every second, this was 1 second, 2 seconds, 3 seconds, and 4 seconds. So every second we had 1/4 of a full cycle. And so you could see me here dividing the cycle into 4 equal parts, and those happen every 4 seconds. Oh, I'm sorry, every second, 1/4 of the cycle. So going back to the definition, the number of cycles per second, so that will be the frequency for that harmonic motion was 1/4 cycle per second. Also, as we mentioned previously, the amplitude, it is 10 centimeters, and it will be the maximum or the absolute value of the maximum negative distance or positive distance. So using those concepts, we could put the definition of simple harmonic motion together. If a point that moves on a coordinate line is in simple harmonic motion, when its distance d, in this case d is going to be the output instead of y, from the origin at time t is given by either sine or cosine functions. So here the letter A is representing the amplitude, and remember we're going to use the absolute value to denote the amplitude. And our independent variable in this case, instead of x or theta, we're going to use t to represent time. And this Greek letter omega looks like a W. It's going to be representing it's going to be actually affecting the frequency and the period for the harmonic motion. So I want to remind you of section 4.5 when we looked at the equation of sine and with its transformation. So it was something like A times sine of parentheses bx minus c. And similarly, A was for amplitude, x was the independent variable, and we had the constant here, b, that was going to help us determine the period. And so what we did to find the period back then was to consider the period of the parent function for sine, which is 2 pi, and we used to divide that by the constant given here, b. And just so you remember, the constant c indicates the horizontal translation or shifting. So using the variables that we have here, and they are still representing real numbers, we're going to consider omega to be the same as b. And when we discussed the transformations in section 4.5, b was determining the horizontal stretch of the graph. If b was larger than 1, we were supposed to have a horizontal compression, which will make the graph from a parent function like that, b greater than 1, will make the graph be horizontally compressed, something like this. So when that happens, we're actually shortening the period, the time it will take to complete one cycle. And we are also increasing the frequency because we will have more cycles per second. Instead of fractions, they could actually be, I don't know, 2 cycles per second. Or if we increase b, or in this case, omega, if we keep increasing it, we could get to something like that, which will be making the period smaller, which by definition will make the frequency higher. So the relationship between period and frequency is one is the reciprocal of the other. So just like we did in section 4.5, we used 2 pi divided by b. We're going to do the same thing here to find the period, 2 pi divided by omega, which is the constant that will be multiplying t. Well, when we're talking about harmonic motion, we're not really going to get that constant. We might have to actually find it. But what we know is that from our previous problem, we know that the period was 4 seconds. And so 4 seconds, I'm going to replace the word period with the formula. So it will be 2 pi over omega, and that was 4 seconds. So to find the frequency of this one, or I'm sorry, to find omega, we will solve for it, and it will be 2 pi divided by 4 seconds equals omega. And why do we already know that the frequency is 1/4. That is the frequency. But we still need omega so that we could come up with the equation of the harmonic motion. Okay, and so in this case, omega will equal to 2 divided by 4 will be 1/2. Pi, or pi over 2. And I did get a little bit ahead of myself, so because the question is coming up now. It is example 6, and it says write an equation for the simple harmonic motion of the ball described in figure 4.60, which is the figure you can see here, where the period is 4 seconds. So they are giving us that information. And so based on the period, we're going to find the frequency. And so since the period is defined as 2 pi over omega, and frequency is actually the reciprocal of the period, so it will be omega over 2 pi. Okay, so if the period is equal to 4 over 1, we could say the frequency will be the reciprocal of that, and that will equal to 1 over 4. Now, we have the choice to use sine or cosine for our harmonic motion, and I want to show you here how we do. And it just depends if you are starting from the origin. So if you're starting from the origin or from 0, from like the middle point between the maximum and the minimum displacement, or I should say the maximum positive and the maximum negative displacement. So the midpoint, if that is in the middle of that, that is a equilibrium point, then I would recommend that you use sine. And so if you were to start from the maximum displacement or from the minimum displacement, and I'm sorry, I said that wrong, from the maximum positive displacement or the maximum negative displacement, then I would recommend that you use the cosine function. So in this case, we are starting from the middle, and so that is why we choose to use the sine function, because the equilibrium happens at d equals 0 when the distance is in the middle, and that is at time 0. And so just to refresh your mind, sine of 0 is equal to 0. So it does make sense. The distance is 0, distance, when the time is 0. This is a time, this is a distance. Since the amplitude is 10, and we know it's 10 from the previous, because it was the same drawing, it is the distance from, or half the distance from this point to this point, and so that will be 20 divided by 2 is 10. So the amplitude, the absolute value of 10 is, well, yes, it will be 10. And so that will be the amplitude. Okay, so far we have that the amplitude is 10, and also that will give us our coefficient of 10, which that will be A. And let me just write here the form that we're going to use for our equation. It will be D equals A sine of omega t. Okay, so the answer of omega is here, and we did find it previously, but let's see how we will do that again. So we were told from the beginning that the period was 4 seconds. And we know that the formula to find the period, it is pi over 2 divided by whatever this little constant of, in this case, omega, will be. So from here, we're going to take this equation. So we have 2 pi is equal to omega, and that is equal to 4. So if I want to solve for omega, I will take it to the right side. So that will be 2 pi is equal to 4 omega. And from here, we will say that omega is equal to 2 pi divided by 4. And so if we simplify this fraction, we will get that omega is equal to 1/2 times pi, or pi over 2. And so that is what we get here. Okay, so that is what we will replace for this variable, pi over 2. We have our independent variable. Instead of x, we have t. It's here. And then we have our amplitude here at 10. So it says here that A will be positive 10 or negative 10. depending whether the ball initially moves up or down. And so I do kind of disagree with the answer on the PowerPoint here, because from the image, they are telling us that if we follow the from left to right, what happened is that the ball moved down and then up, but that's just a matter of how you interpret the I guess the order of the two pictures, because it also could have been it started here at the maximum positive distance, which is 10, then it went to the middle, and then it went all the way down here, and then it moved way back up. So we're just going to go with whatever the PowerPoint says here. If you run into a problem while you're doing your homework, don't hesitate to send me a question. So we're just going to keep it like it is there, and it will be equal to 10. So the equation will be D equals to 10, I'm just rewriting what's here, times sine of pi over 2 times t. That will be the equation. Okay, now to find the frequency, it's very simple if you just take the reciprocal of the period, which is 4. So the reciprocal of the period is 1/4, right? The reciprocal of 4 over 1, we already mentioned, will be 1/4. So that's the way to find it. Now, if you don't know what the period is, but you know the equation, for example, if you are given the equation, so you know what omega is. So if you don't know what the period is yet, which you could find, but you could also use the formula for frequency, and you will use omega. I'm just going to rewrite what's here. Divided by 2 pi. And so if we do this and we multiply the two quantities, the outer quantities, well, this is 2 pi, omega divided by 2 pi, we will get 2 pi. And then here we will get 2 times 2 pi, that will be 4 pi. And I feel like I'm doing something wrong. Because this will give me 1/2. So I found my mistake. I wrote a 2 here, which is not correct at all. So let me fix this. So we erase this here. And let me just do this again. So I'm just going to rewrite this fraction, but in this form. So omega is pi over 2. And then we have to divide by 2 pi. So that is 2 pi divided by 1, which will equal to pi times 1 is just pi, and then 2 times 2 pi is 4 pi. And we know that pi divided by pi is equal to 1, so the answer to this is 1/4. And so that is the frequency, which is every second 1/4 or 1/4 of a cycle is completed. Other examples of harmonic motion, we have the illustration here, and is in the wave motion that results when a stone is dropped into a calm pool of water. The waves move outward in roughly the shape of sine or cosine waves. As an example, suppose you are fishing and your fishing bobber is attached, so that it does not move horizontally. As the waves move outward from the dropped stone, your fishing bobber will move up and down in simple harmonic motion. And that is the pattern that we could see here, shown in figure 4.62.